This is the first part of the revision video on ultrasound. We're going to be looking a bit more broadly than ultrasound, really. We're just looking at the idea of using a pulse echo sequence to determine the range of an object. So firstly, let's just have a quick look at what ultrasound is. So we'll focus mainly on ultrasound, although this does apply to other types of waves. So ultrasound, firstly, you know it's a sound wave, so it's longitudinal, which means it oscillates as wavefronts going in this direction, and oscillates the particles going backwards and forwards in the same direction as the direction of propagation. Secondly, it's got a frequency which is greater than 20,000 Hertz, which means that it is inaudible to the human ear. Hence it being ultrasound, as in ultraviolet is above the visible range in the spectrum, the electromagnetic spectrum, so ultrasound is above the audible range in our, I suppose, our acoustic spectrum. So how do we use that then, these high-pitched, high-frequency waves, to determine distance? Well, we're going to look at something called a pulse echo sequence. Which is a really simple sequence, and what has to happen is we need to use something called a transducer. A transducer is a device which changes electrical signals into mechanical signals. So in this case it's going to change an electrical signal in the form of a voltage into a vibration, which is, you know, it's a sound wave. So we're going to show these as longitudinal waves. In fact, it's easier for us to show them as a transverse wave, but remember they are longitudinal waves, so I'm going to draw them as these are the longitudinal vibrations here. And that's going to be emitted as a pulse, which might be a very short sequence of waves that are emitted from the transducer. And it's not a continuous sequence, it's just a short pulse. That's important. That wave is then going to travel. It's going to propagate through our medium. So we've got a medium here. And when it reaches our target, in this case we're going to be shooting it at a wall, it reflects. And hence the name echo. So you've got pulse, echo. And that echo then returns in the opposite direction and is detected again by the transducer. Now, why does it reflect off here? Why off this particular bit? Why not from the air, or why not from within inside the wall? Similarly to our light and the idea of having different refractive indices, and it reflecting or refracting at that boundary, at this interface between the medium, which is air, medium 1, and a second medium, actually it's to do with both mediums, or media, here, it's this difference in density which causes the reflection to occur. Now, not all of the energy will be reflected, not all of that wave will go back, some of it will propagate through into medium 2. And it depends on the densities, the relative densities of medium 1 and medium 2. So the density here is important, density 1, and the density here is important. And roughly, if they're equal densities, then that, as it is in light, that boundary, that interface isn't really seen. So we'll look at that idea and why that's important later on. If they're very different densities, like our air and our brick for our wall, then we're going to have very different densities, and we're going to have a lot of the sound being reflected back towards our transducer. So what our transducer does is it knows a certain key fact about this wave, and it knows that the speed, in air anyway, is going to be around 330 meters per second. Now that's going to vary whether it's in solid, liquid or gas. If it's in a liquid or a solid, then it's going to be up to maybe 1,000, maybe more meters per second, but in gas it's relatively slow. Space in between the particles is larger, so we get a speed of around 330 meters per second. Now what our transducer does, let me just spell that for you on here so we've got that written down. What a transducer does is it converts those signals and it then converts them back the other way. When that pulse is received, when the echo comes back to the transducer, the transducer changes those vibrations into an electrical signal. And that's what the sonographer, the person who's going to be doing the ranging experiment, will see. And what they'll get is some amplitude, initial amplitude, so we'll call that A up here for amplitude. They'll have time along here, and they'll know that they've sent out a pulse. Let's call this t equals 0 here. And a certain time later they're going to receive a pulse back. Notice this is time on here, not distance. And that time between there and there is important because using the equation speed equals distance over time, we can use the speed from up here, the time between these two, so this time here, and therefore we can work out the missing distance. Okay, so this is our emitted pulse. And this is the detected echo. Now again, you'll note that the amplitude of the detected echo is somewhat smaller than that of the emitted pulse. That's for two reasons. One, some of that sound energy will have passed through into medium 2. Secondly, we're going to have some energy absorbed as it travels through the medium. Again, that will always, nearly always, make for that second pulse, certainly that pulse, to be lower than our emitted one. We'll look at a slightly more complicated diagram in a minute for how we could use this for a situation where it's not just range finding from one interface. So let's say then that time that we've got here was equal to 2 milliseconds. So that means the pulse has gone out from here, reflected off our wall, and returned 2 milliseconds later. At that point we could start the whole sequence again, and it's important to understand that we have to wait for that pulse to come back before we can send off our next pulse, and we'll think about that again in the next video. So let's do the calculation then to work out how far away this wall is. We've got V equals D over T. Okay, V for our speed of our wave, we tend to use V for that rather than S. It doesn't really matter what symbols you use as long as you make it clear to the examiner what you're doing. So I then put our numbers in. 330 equals distance over 2 times 10 to the minus 3, so it's 2 milliseconds. Rearrange all that, you get distance equals 330 times 2 times 10 to the minus 3, which means we get a distance of 0.66 meters. Now that's not our final answer, because that distance is the distance that the sound wave has travelled there and back, because we've timed it for the timing as it exits, as it's emitted, reflected, and then returns. So in my exam I'd write something along these lines, show the examiner you understand, but this is distance there and back. So the wall is 0.66 over 2 equals 0.33 meters away. And that's how a pulse echo sequence is used to determine distance. Now that would work with radar, it could work with microwaves, it doesn't really matter as long as you're able to get a reflection off a boundary or an interface between two things, then you can use this particular sequence. Applications of this we're going to look at in the next video. If you want to go back through this, then rewind and have a look at it again. The pages in the textbook are pages 108 through to 113. So go away, have a look at that, and do some past paper questions on it from your booklets.